Okay, so welcome everyone. Thanks for coming. Today we're delighted to have Dr. Tamara Kolda from Sandia National Labs as our speaker. Dr. Kolda has been at Sandia National Labs in California since 1999 and is a distinguished member of the technical staff. Her research is in the broad area of computational engineering and data sciences. Her work in tensor decompositions, graph models and algorithms, data mining, numerical optimization, linear algebra, high performance computing, and scientific software has been cited over 19,000 times. She co-developed the widely used Tensor Toolbox for MATLAB, as well as many other scientific software packages. Recognitions for Dr. Kolda include a 2003 Presidential Early Career Award for Scientists and Engineers, an R&D 100 Award, and 3 Best Paper Prizes at international conferences. She was elected as a Fellow of SIAM in 2015, a Fellow of the Association for Computing Machinery in 2019, and a member of the National Academy of Engineering in 2020. She's active in professional service. She's currently an elected member of the SIAM Board of Trustees. During her time on the board, she helped to develop the SIAM Journal on the Mathematics of Data Science and serves as its founding editor-in-chief. She's also a member of the National Academy's Board on Mathematical Sciences and Analytics. With that, Tammy, I'll hand it over to you.
Thank you, Jordan, and thanks to the committee for the invitation to speak today, and thanks to everyone who's here virtually. I will try to take breaks every so often to pause for questions, and this way you can be engaged throughout instead of just at the very end, and it helps me to feel like I'm not just speaking all alone. So I'll come to like pause points. Of course, if you have questions before then, I think you can put it in chat and someone will read it to me, or otherwise when we get to the break, we'll go ahead and go these little breaks throughout. We'll go ahead and go through any questions that have popped up, but just warning you now that there will be questions. I'll ask for questions before the end. So this is a talk on practical leverage-based sampling for low-rank tensor decomposition. I will explain all these terms, so don't worry if they're not familiar. And this is joint work with Brett Larsen. So here's his mugshot. We were funded by the Department of Energy, Advanced Scientific Computing Research, and Brett had a fellowship from the DOE called the Computational Science Graduate Fellowship, and the work is available on archive if you have questions. I also sent, I think it was Jason, the link to my slides. If you want, Jason, you can put it into the chat if anybody wants the PDF to follow along. So tensors are multidimensional arrays. So a matrix is a 2-dimensional tensor. And then we're talking about things that are 3-dimensional or third order is what we often call it, or higher. And these kind of data structures appear in many different applications. They appear in chemometrics. It's actually tensor decomposition has been widely used for many decades for fluorescence spectroscopy. Here we have a 3-way tensor that's emission by excitation by sample. So each time you do an experiment, you get out a matrix. When you do many experiments, you get sort of a pile of matrices, and it turns out that tensor decomposition is the perfect tool for analyzing that type of data. I've been involved in joint research with Stanford, where we used it to analyze data coming from neurons, and it's been a very nice tool for that. We've looked at crime data from public reports out of Chicago. I've looked at, actually Sam Sherman is here. She's co-author on some nice work on looking at tensor methods for multivariate Gaussian mixture models using higher order moments. And then there's all sorts of other applications. So there's many places where tensors appear. The thing to know is that what it comes down to is tensor decomposition is a tool for finding patterns in massive data. So it's a form of unsupervised learning. All right, so we have some data tensor. Because of some notational situations in this talk, I'm just going to say this tensor X is a d+1 way tensor. Just turns out to be convenient for some stuff later. So it has d+1 indices. What we're going to get out is d+1 factor matrices. So we're going from a huge data array to just a collection of matrices. So if you think of this as like n by n by n, so it's n cubed. If n is very big, that's quite large, down to something that's just n by r and there's just D+1 copies. So that right there is a big data reduction. So that's one reason why these things are interesting. So we get out a collection of D+1 factor matrices. Each of these has R columns. That's a model rank. That's something that you can think of the user picking. So that's how complex your model will be. And the number of rows in each of these factor matrices is equal to the size of the corresponding dimension of the tensor. So these factor matrices are put together into a model of the data. And this model is constructed by taking outer products, tensor outer products, of matching columns. So we take the first column in A1, A2, all the way up through AD+1. So in the three-way case, we just have 3. And we get an outer product here. And then we do that again for the second columns and all the way up to the rth columns. And we sum those up to get our model. And so there's this sort of complex mathematical expression for that, which sort of tells you exactly how we match the elements to the data and compute from those to this. You don't have to know all those details for this talk, so don't worry about that. So just know that we go from data to factor matrices. So before I get into the math, which is going to be great fun for us mathematicians, but at the same time requires a lot of heavy lifting, I want to give you a reason to sort of pay attention. So I'm going to start with an example. And so that example is looking at analysis of Reddit data. Of course, we did this analysis a while ago, but Reddit was just in the news. So, you can imagine where this type of analysis could be useful. So if you don't know what Reddit is, it's a discussion forum, and there are subreddits which are focused on particular topics. And some folks, Shaden Smith and others, set up a tensor that was organized as looking at who talked about what, so what words did they use and which subreddits. And they built a three-way tensor that had 8 million users, 200,000 subreddits, and 8 million words. And so the IJK entry of this tensor was the log of 1 plus the number of times user I used word J in subreddit K. So we just take the log because it's just sort of something that is often done with counts, and you add 1 so that if there's no combination IJK, it's 0, so log of 1 is 0, so it goes back to 0, and everything else is just some positive value if there's any activity in that combination of user, word, and subreddit. This tensor only has 4.7 billion non-zeros. That is actually a tiny fraction of the entries of the tensor. So it's only 10 to the minus 8% of the entries are filled in. Even then, it still takes 106 gigabytes to store this tensor. So we're storing the 4.7 billion non-zeros, and then each of those non-zeros, we have to store the I, J, and K. So it takes 106 gigabytes to store that. And then we're going to compute a rank 25 decomposition, and I'll show you what we get from that. So just to give you a sense, I'm going to normalize all these components, and I'm giving you the relative weights of those. So the biggest one, you can think of this as the norm of that thing, is around 7,500. The smallest one is around 3,000, just so you get a sense of what the relative importance of these are. They're all roughly within a factor of 2. This model explained just 6% of the variance, but so we could do a higher rank model, but this is just sort of to show you what's going on. And this is not so unusual that the variance explained is kind of low for these highly sparse models, because a lot of the pieces are just kind of outliers. So then I'm going to zoom in, just for the sake of argument, on component 6. So there's 3 vectors I need to show you, and they're really big vectors, so I can't show you the whole thing. So one of the vectors corresponds to the users. We're not going to really dig into the users and look at them. I'm just going to kind of give you like the profile of the drop-off in the user activity in this component. And then the more important thing is the subreddits. Now there's like 200,000 of those. I'm only showing you the top few. And these are color. Well, first let me say, just look here. We have things like World News, Europe, Today I Learned, and so on. These are the titles of these subreddits. They're color coded by the overall frequency across all the data that was collected. So by far, Ask Reddit is the most busy of all the things by a huge margin. Everything else you'll see is blue, because there's Ask Reddit and there's everybody else, sort of exponential difference. But the darker the blue, the less frequent it is, and in some sense, the more significant it is that it shows up. And then we did a similar thing with words. These are color coded also by overall frequency using the same color coding. Here we see more of a distribution. And so red and brown words are very common, like one appears in many discussions, but some are less common, like in blue, you see country and world. And it's not surprising that those are terms that are frequent in a subreddit that seems to be about world news. So hopefully this helps you understand the kind of information we're pulling out from this huge 3D array. We're getting sort of groups of subreddits, words, and the users. And so we can see some of the patterns we saw. So we saw this one, international news. We also, if you zoom in on number 8, this one we're calling relationships. The first group in this is relationships, and you see relationship advice and other sort of relationship-y type things. And then some of the words are sort of relationship, friend, tell, and talk, and someone. I think this sounds very pleasant. I guess I haven't really read it, but these sound like nice discussion topics for relationships. Then we have politics. So this data is from 2015. So there was a presidential election going on. Bernie Sanders was also a candidate then. So the top one is politics, but the next we see Sanders for president, political discussion, and we see things like state and vote as some of the key words. There's always like, among many of these, there's like people don't. I guess I should spend more time on Reddit. It sounds like fascinating conversations about what people don't do. This one is very distinct. It's sports. Here we have NBA, NFL, fantasy football. We see things like team and player and fan. Then we see, more specific sports, wrestling, soccer. All of these, we actually have them in the appendix of the paper. We have every single one of these 25 that we computed. We even went through and sort of blanked out the swear words so that, because there's actually a lot of swear words in Reddit, so we kind of blanked those out so we could put them all in. This one I kind of like, it's movies and TV, and it's actually more specific than that. So movies and television are first, but then you see sort of a sci-fi slant, Star Wars, comic books, Marvel Studios, and then the top words are things like movie and character and film and watch. So these are some of the things. And then there's sort of card games. We're sort of debating back and forth, Brett and I. First he thought it was a computer card game, then we found out maybe it's also a regular card game, but there's Hearthstone of the Storm, and other types of card games. And you see things like card and deck and player and win and turn. And so these are the discussions that are happening there. So this is the kind of information we can get from this truly large scale data set. So how long does it take to compute that? So it's a tensor with 4.7 billion non-zeros. It takes 106 gigabytes of storage. If we run it with the standard approach in MATLAB, you can do a little better if you go out of MATLAB, but it's 96 hours for a single run. We actually ran it 10 times. So this was a heroic effort on the part of Brett. It might be the longest running MATLAB job that I've ever been involved with. This takes 96 hours. If we use a randomized method, we can get there in only 8 hours. So this is a 12 times speed up. And this is a big difference in being able to validate your model, do multiple runs, even do a single run. That's a lot of time. And so I'd like to show you how we got from 96 hours to 8 hours, and moreover, have a lot of confidence in the quality of this and the ability to do this in other situations. So I'll stop here for any questions about sort of this motivating example, and before I kind of dig into a lot of the math details of how we did that. I'll take that as no questions so far, so great. All right, so come back to this tensor decomposition. So this is sort of where we started, but we're going to actually just focus on the way that we solve it. Is we solve for just one of these factor matrices at a time. And then it reduces to a least squares problem. And so I don't want to focus too much on the tensor decomposition. I kind of want to jump to the least squares problem because it's about 4 slides to tell you how to get between those two. And by that point, we've all fallen asleep. So I'm just going to skip to the least squares problem. So the least squares problem, and this is kind of what I want you to remember. This is kind of our focus today, is we're going to have least squares of the following form. It's a tall and skinny matrix Z of size big N by little r, a matrix of unknowns of size little r by little n. And so we have multiple right-hand sides typically. And so, but don't worry too much about that. Most of the details don't work just as well with little n equal to 1. And then we have a right-hand side, which is a version of our tensor, which might be very sparse. So if we link it back to the tensor problem, this Z is what's called a Khatri-Rao product of all the factor matrices but 1. Don't worry if you don't know what that is, I'll tell you in a minute. And the number of rows in this big N is the product of all the numbers of rows of these separate matrices. This B matrix is the factor matrix we're solving for. So just for the sake of argument, I'm assuming we're solving for the last one. And so that's our B. And then our right-hand side is a version of the tensor with all the elements reordered in such a way that the number of non-zeros stays the same. For instance, all the same values are there, they're just kind of set up into a matrix. So just even creating this thing from the factor matrices cost big N times R to form. Solving this system in general is the least squares problem. It costs big N times little n times R squared to solve. There's a trick we can do because of the special structure of this that takes out one factor of R, but that's so small it doesn't really matter. Big N is our issue. It turns out because our problem is sparse, there's some other tricks we can do that actually makes this get reduced down to R times the number of non-zeros in X. So that sounds promising, but in our case, we're in trouble either way. So for Reddit, just for mode 3, which actually isn't the worst mode, but just so I'm not being, so it doesn't seem like I'm being unreasonable. Mode 3, N, the big N is 1.2 billion, and the number of non-zeros is 4.7 billion. So either way, we're at order a billion, and that's quite large. And that's why it takes 96 hours. So this is the problem we kind of want to tackle here. All right, so don't worry about the tensor origins. Just know that we have this least squares problem. We have this Khatri-Rao structure that I'll tell you what that is. We have our unknowns, and we have our right-hand side, which might be sparse, which I'll explain why that matters in a couple of slides. All right, so what is this Khatri-Rao product? So we have our factor matrices, and the way it works is that each row of this Z corresponds to the element-wise product of a unique set of rows from these factor matrices. So we just take every possible combination of rows, element-wise multiply them together, and that gives us a row of Z. And so it doesn't matter exactly how we do it, but there's a one-to-one correspondence between the rows here and sets of rows in the factor matrices. And then, there's a formula here. This is just sort of in MATLAB notation. Well, actually it should be dot star. So this is Hadamard product. We're just multiplying all those rows together. And then there's this specific formula for how you map between the indices of these individual rows and indices of this. And it's sort of what it turns out is each column here is a Kronecker product of the corresponding columns in these factor matrices. All right, so what are we going to do? We're going to put together a bunch of ingredients to solve this problem using randomized methods or matrix sketching. And we're going to step through those. If you just kind of try to do things naively, a bunch of things fall apart. And it wasn't just one ingredient or two. We have 9 ingredients in the end to make this efficient. So hold on to your hats as we sort of go through these. So the first one is the one that's sort of the main idea. If you remember nothing from this talk except this, it's that when you have these tall and skinny problems, you can do what's called sketching, and you can get a reduced system. And so I forgot to say earlier here, this is really tall. I mean, my slide is only so tall, so I put these dashed lines. Think of this as the height of a skyscraper. It'll give you a better impression. And we're going to reduce it down to a very tiny system where we went from big N to little s by multiplying by a matrix omega that does our sampling for us. And so we're just going to sample a subset of these rows and the corresponding rows of the right-hand side and get our reduced system and solve that instead. And there's a couple of key surveys you can look to for information on that. But whenever you have a tall and skinny problem, you should be thinking maybe I can do some sampling or sketching to reduce my problem size. So, okay, so we're going to do that. so the first thing we have to do is how should we set things up so that this subsystem, the small system we get, is equal to the big system in expectation. So we're just going to start with the easiest thing. How can we make sure that it's equal in expectation? And then we'll talk about how to make sure that we can bound the error of the residual when we solve the smaller problem. All right, so let's just suppose I have a probability distribution on the rows. I'm not saying how that's selected yet. It could be the uniform distribution. Okay, so but just I have some probability distribution. And let's say I only pick one row. I'm gonna sketch it with just one row. That's not a good idea, but let's just say I did that. I just want it to be correct in expectation. What do I have to do for omega? So I pick xi as my single index, and I set up an omega that has one row because S is 1, and it's all zeros except for the xith entry, which is 1 over the square root of the probability corresponding to that entry. So then, assuming that every row has positive probability of being picked, then I can say that the expected value of this system is equal to the value of the that I get in the whole thing, because the probability of picking that is pi, and I multiply it times my sampled system, which just picks out the ith row, and it weights it by 1 over square root of pi. But when I pull all that out with the square root, it cancels out. I sum it over all possible rows, single rows I could have picked, and I get back my original system. I'm sorry, I realized I changed the notation here to alpha and eta instead of the b and x, but those are the same thing. Now, if we pick S random indices, the logic is much the same. I haven't told you how S is chosen either, because how big you choose S is going to be part of the theory that we sort of developed, and how to pick the probabilities, those kind of go hand in hand. But assuming you pick S of them, it's almost the same as if you pick a single row, except for now it's all zeros, except for one entry, which is 1 over the square root of S times that probability. So each row of omega has just one non-zero. That means it just samples a single row. And you are allowed to sample the same row more than once. And as before, the expectation works out. All right, so how do I pick these P's and how do I pick this S? So let's first talk about the P's. So P's are going to depend on something. P's are going to depend on something called leverage scores. So the leverage score of row I is a funny thing. You take an orthonormal basis for the column space of your matrix, and the leverage score is the 2 norm of row I is the 2 norm of this orthonormal basis matrix in row I. It's I think very non-intuitive for me, but you can say that thing is between 0 and 1. That's easy to show. And then the coherence is defined as the maximum of all these scores. So if they're all between 0 and 1, of course, the maximum is less than 1. But you can also go ahead and prove that the minimum is at least as big, the maximum leverage score is at least as big as the number of columns divided by the number of rows. And the rough intuition here is that any row that has a high leverage score is very important in your least squares problem. So what does that kind of mean? So if I had a matrix Z, and then most of the elements were in one of the columns were 0, except for 1, all of these are 0. The only way I can possibly get a correct solution for alpha 1 is if I pick row 1, because none of these other rows tells me anything about the solution for alpha 1. So it means that row 1 is important. And in fact, as an exercise, you can sort of convince yourself that the leverage score of row 1 will indeed be 1. So that row is important. If you don't have it, you have essentially no possibility of getting a correct, any bound on what alpha 1 should be. And so if I know the leverage scores and I choose my PIs in some way, then I can actually bound the number of samples as a function of the probabilities. So these samples kind of depend on the error that I want. So that's our epsilon, the number of columns in the system, and then this beta term, which depends on the ratio of these PIs, which I get to specify, and the leverage scores, which are what they are for this matrix. So if we did uniform sampling, if we had a matrix where the coherence was very small, so we call that incoherent, if it's close to R over N, then our beta actually turns out to be 1. That's the best we can do. And so our samples are just sort of proportional to 1 over epsilon squared times the number of columns times the logs of the number of columns. That's the best we can do, so we're happy. But if any of these rows has a leverage score of 1, then the number, and we were still to do uniform, then we would actually need order number of the rows in the matrix samples to have any hope of getting something right. In fact, it's even bigger than that. So of course we wouldn't want to do that. In that case, we have to do something smarter. Our ideal would be that we choose our probability to be exactly proportional to the leverage score, just divide it by R to get it to be a probability, but we can't compute these leverage scores in general. They cost too much. So as an aside, you might think, well, why don't we just try to make things incoherent? That would be the best thing, and it would. I totally agree. We've done some work on this already, where you can sort of, before you start to solve the system, do what we call mixing, where you mix up the rows of Z and the corresponding rows of X in such a way that you can pick any of them. So this has been called many names. Michael Mahoney has written a lot on this, calls this uniformizing the leverage scores. It can be achieved by multiplying by just a random matrix, where you pick every entry from a Gaussian distribution. That, of course, is kind of slow. You can also do something called a fast Johnson-Lindenstrauss transform. So you're doing FFTs on every column. That is guaranteed to give you something pretty close to optimal in terms of the number of samples that you need. It's not much worse than just doing multiplying by a regular Gaussian matrix, but you have faster multiplication. That still involves big N's. That was too expensive for us. We worked on something that looked at the structure of Z and its Kronecker product structure and made up a special sort of transform. But I don't want to go into the details of that. I'll just point to some references. We sort of came up with the method, but we couldn't quite analyze it. And then later on, I worked with some folks at Texas, Ruhi Jin and Rachel Ward, to analyze it. And then at the same time, a couple other groups, including Malik and Becker at University of Colorado Boulder, came up with analyses to show that this thing was indeed a good sort of unifying formizer from not only a practical point of view, but also a theoretical point of view. But we can't do that, because if we did that with a sparse right-hand side, we'd get a huge sparse right-hand side. And we can't afford to form that in the problem that we're working on. So the next thing we consider is, all right, I can't compute those leverage scores. They're too expensive. But instead, we can get upper bounds on them. And it turns out that that will actually be something that will be helpful to us. It won't be as good as having them exactly, but an upper bound will be something that we can work with. And we can upper bound them by looking at the leverage scores of the corresponding rows in each of the submatrices. So the leverage score of this guy is upper bounded by the product of the leverage scores of these individual rows. So that's a result that we had actually proved in the original work, and then actually another group had proved it simultaneously. And so that is a bound that exists, and we can exploit that in this leverage score sampling case. All right, so the main theorem we get is you have this system you want to solve, and it has this special structure in the right-hand side. We define our sampling probability to be proportional to the product of the leverage scores of the corresponding factor matrices for each row in this Z. And those leverage scores come from those individual factors. Then we're going to do a random sampling of S indices. I haven't told you what S is. S indices, and use the way of setting up the sampling matrix so that the expectation is correct. Then we're going to solve the sample problem and get a B star tilde. So the tilde means it comes from our subsample problem. It's the optimal solution to our subsample problem. When we plug that back in to the original problem, the residual is within 1 plus epsilon of the original, of the optimal solution to the full problem, with probability at least 1 minus delta, where the number of samples depends on this epsilon, and this delta in this format here. And the thing that you'll notice if you think about these things a lot, which I don't, but some of you might, is it's r to the d times log of n divided by delta divided by epsilon squared. So if it was optimal, this would be r. And so we have instead r to the d. But it's not a bad price to pay for these really large problems when r and d are relatively small in comparison. All right, so questions here. I also saw there was maybe a question that popped up in the beginning. So if there's any questions on this part so far, that'd be great. And maybe I'll take this question from Gabe. It said, can you explain again why the less frequent words were more important? So I guess I was trying to argue that it's not that they're more important, that they're more unusual. So for each factor, the word, I think, people appeared in almost every factor. So it wasn't maybe so distinctive. Maybe I shouldn't have said important, maybe I should have said distinctive. What is distinctive about those factors? So the combination that it was important to that component and an infrequent word made it in some sense more distinctive. If you could let me know if that sounds good or if that leads to a further question, that'd be great. Any other questions or signs of life from the ether? All right, I got a thumbs up. Thank you, Jason. All right, so I will march on. So we're not done. We got 4 ingredients out of 9. So what's the next thing? Well, we want to sample according to products of leverage scores. But if we compute all of those, we've now computed n things. We're back where we started off with this big N calculation. So we don't actually want to do that. So we're going to sample without ever forming things. And what we're going to do is we're going to sample separately from each of these factor matrices. So we'll sample this one according to the leverage scores that it has. Then we'll sample the second one according to its leverage scores. And the last one according to its leverage scores. It turns out that this is legal from a sampling perspective. You can sample one at a time, and the combination is equivalent to as if I had computed all those probabilities and I sample all at once. It's sort of a fun exercise to work that out and show that that's the case. So that means it's much easier to calculate that. And so that enables us to do the sampling according to this distribution, which is cheap to compute without actually forming all these products explicitly at any point. Oh, sorry, and then I can multiply those together to get the sampled row. And so that's actually what we do. All right, so there's a couple things we worked out that are not specific to tensor problems. It can actually be used in any situation. So one thing that we found was that sometimes a particular combination was such a high probability combination, it was such an important row, that when we did random sampling, we sampled the same row over and over and over and over again. And it turned out that even though we had a very big matrix with a large number of sampled rows, if half of those rows are actually the same row, you're not really getting more effective power out of your samples. And so, what do I mean? So just looking at one of our problems, and the details are sort of in our paper, if we define a set D to be all the indices that have probability greater than some threshold, and we played around with this threshold, but we found it's usually useful to take it 1 over the number of samples in this whole thing. So how many rows have probability higher than 1 over S? In this example that had 10 to the 12th, order 10 to the 12th rows, 15,000 of those rows accounted for 51% of the probability. And so that meant when we did these 2 to the 17 samples, we'd actually be seeing a subset of all these rows repeatedly and much more frequently than the rest. Those would account for half of our samples. And then we see this pattern repeated in a lot of situations. I don't want to go through all these details here, but just to give you a sense of what the distribution of those probabilities, if we did multiply them all out, look like, and this is super teeny, but it's a log scale. And so some of those rows are super important. We definitely need to sample them, and we're going to sample them a lot because their probability is high, relatively speaking. But how do we, but then we get a bunch of repeated rows. And so if we just combine repeated rows that we've sampled before we solve the least squares problem, then it's a huge win. And so this is something you can do with any leverage score-based sampling regime. It doesn't have to be specific to tensors. So when you're using leverage score-based sampling, it's usually because you need to be uneven and some rows are more important. But if you just do direct sampling, you'll just keep sampling the same thing over and over again. And we saw that this easily gave us a 2 to 20x speed up and at almost no cost. This is a little upfront stuff, and then it reduced the linear algebra requirements subsequently. And so this is a really easy step, and it was just a matter of working out sort of the details of how to combine things and make sure all the probabilities are retained in a correct way. But this is possible to do. All right, so ingredient number 7 out of 9. If some rows are so important, you might ask, why don't we just include them deterministically? And there actually have been past approaches which figured out these probabilities and then just used the highest ones. They didn't sample, they just took the biggest ones and solved from there. And that's a valid approach, but there are sometimes advantages to doing it randomly. You get some stuff that you might not normally see. So can we do a combination? And so we're like, yeah, you can do it. There's a lot of sort of details you have to work out to get all the probabilities correct, but we can include the very highest ones deterministically. And so if you set some threshold tau for determining including it deterministically, we get a set of those rows that are included deterministically. And then we can calculate what probability those are. And I just was showing you some examples of what those probabilities might look like. And then we just add those rows to the top. Then we can sample from the remainder. It's a little bit complicated because now we were computing those probabilities implicitly. So sampling one row, then sampling another, then sampling another. We might get one of those high probability rows by accident. So we do what's called rejection sampling. If it was in the set, then we reject it and we keep sampling until we get one that's not in the set. And then we have to adjust the weight that we picked at appropriately and then add that in an appropriately weighted fashion. So that's what all this business is here. But so that's sort of, you can do it. It just takes a little bit of extra sort of probabilistic thinking to work out all the details. All right, and then ingredient number 8, we had to find those high probability rows. Again, we don't want to compute those probabilities. We want to find this set of high probability rows without actually going through and computing all of them. And so the way that we do it is we just compute, sort of the biggest values here. And so if this is 0.3 and this is 0.2, and we have some tau, if we take this value down here, these are sorted according to their size, all these leverage scores for this one, we sort them according to size. If this value times these highest values is less than tau, then we know that nothing below it will be in there. So we do that kind of for each one with the other ones at their highest value. We can get some cutoff of values we must consider, and that's usually a big drop off right there. And then we just take the products of all the remaining ones and just take those that are over tau. There are many other ways you could do this, and there are actually smarter ways to do this calculation that we could also incorporate. But the point is to do it without calculating everything. And the last one I'm just going to sort of gloss over is we have this right-hand side, which is a big sparse tensor that takes 108 gigabytes to store. We have to pull out the sampled right-hand side from that. And that can take a long time to do as well. It's data movement is usually actually the most expensive thing in a calculation. We're going to be, rummaging around this 106 gigabyte object and pulling some data out. So we worked on some ways to do that. We never actually form this unfolded version of the tensor. We do a lot of pre-computation up front to make it fast, to pull things out later. And then the result we get is a sparse right-hand side. And so So we just know that we did that, efficiently, and then we can sort of talk about details later. And then before I show some of the numerical results, I just want to stop and see if there was any questions. And I see one did popped up, and I welcome other questions. I'll go ahead and read this one. So this is from Jamie Haddock. When you update a single factor matrix and must update its leverage score, is there any fast way of calculating the updates to the scores using the calculated update to the factor? So that's a nice question, Jamie. Thank you. I guess I haven't thought about it. It's pretty cheap, and even for this relatively big one, I'd have to go back and check the breakdown of the calculations. But I think that's actually a nice question, and maybe we could talk about it, and I'll try to think about it more later. Yeah, normally, because we're doing a least squares problem, we don't really calculate it as an update to the factor matrix. It's more like just a new factor matrix. But it does beg the question if we could do something by understanding the difference between the two and make a faster way of calculating updated leverage score. So if you have ideas, that might be fun to brainstorm about. Any other questions? Would there be a non-negativity constraint for the least squares so that factor matrices are non-negative? So this is a really good question. So thank you, Josh Fendrell, for that question. We actually were planning to do that when we started this project, was to also add non-negativity constraints. We didn't do it. So that is still a thing that has to be worked out, but I think it would be super useful. And so the challenge is kind of going back through and pushing through all the theory for the non-negative case. But I think it's really a good problem and a really relevant problem, because a lot of people do this with non-negativity constraints. So that's a great question and a great idea for something to do. Any other questions? All right, yeah, thank you for these questions. We're getting towards the fun part, at least in some ways, the numerical results. So we worked out all this theory, and it looks like it's just 9 slides or 9 ideas, but of course this took a couple of years and many months of effort to sort of walk through all these problems that we run into. And this is sort of often like the game with randomized methods is you have to have a really big problem for them to make enough of a difference to be worth it. And even if you're you're convinced they're worth it, there's a lot of theory that you have to work through, and it normally you need some help. In my experience, at least, it's reading a lot, but it might also be engaging colleagues. It might be bringing other collaborators who can sort of help work through all these problems that you encounter. All right, so some numerical results. So first of all, I just want to kind of convince you of what happens as you pick more samples. So this is one of our subproblems from one of our tensors, a relatively small one, so that we could actually calculate the true solution. So n is 46 million, so the number of rows in the big problem is 46 million. R is 10, so we have 10 columns, and we have 183 right-hand sides. And then we solve the sampled system. And then we also solve the full system so we can compare. That's why we couldn't make this too terribly big, because we had to be able to solve the full system. And then we calculate, if you plug the solution of the sampled system back into the original system, and you look at the relative error. So we just put 1 in there in case it was really, in case this original one was really small, but you can ignore this. So this is the relative error from the best possible solution to the full thing to plugging the solution from the sampled problem into the full problem. And what's the error? And so, first of all, I just want you to see that at 4 times 10 to the 5th samples, the error is getting down in the best case towards 10 to the minus 5. So sometimes I think randomized methods have a bad rap that they can't push the error down more than a couple of decimal places. And I want to show you that it can get actually pretty good. So, and then we mentioned that there was this just random sampling approach. So you can sort of see we're flatlining here. And this is because there are a few higher probability rows that are overwhelming our system. We're not getting much benefit from increased samples because we're actually just sampling the same rows over and over again. So if we switch to this hybrid method, we get a much better reduction because our samples are more effective. We're actually getting more unique samples. And so, there's this nice benefit to sketching, period. You get reasonable accuracy in many cases, And then you can actually get, with this additional of this hybrid approach, you can get even better performance relative to your number of samples. And so this was a problem small enough that we could do a lot of extensive calculations like this. And then, why is it happening? So if we look at the number of samples, as we increase those to 2 to the 19, the percent that comes from deterministic is getting up as high as 20%. Here it's 15% for this last one. And so 15% of the samples are deterministic. That's actually accounting for 90% of the probability in our, if we had selected among all the rows, which means that these would have been sampled many, many times. And so you're actually not getting additional information when you sample the same row over and over again. And so that's why it's not very interesting to do that. You don't get as good at convergence. So this hybrid method of deterministic and random sampling is really nice. And I suspect I'll get a question about why not just do sampling without repeats. And we actually spent a lot of time on that. It's really hard to get the appropriate weighting in that case. I think it might be impossible to do in reasonable computational time. And so that's why I do sampling with repeats. And you can do this deterministic hybrid thing was sort of our compromise on that. All right, so I showed you results before for one tensor. This is actually a different tensor. So this is an Amazon tensor, which is also huge. It has 1.7 billion non-zeros. It's a three-way tensor. It's 4.8 million by 1.8 million by 1.8 million. And its big problem took 7.9 hours to run. So this was our medium example for when we were debugging things. So 8 hours to run the full method. Here we ran, I'm just showing you results from the hybrid deterministic and random sampling one, but they're all kind of similar if you look at the paper. But this is getting down to just 40-ish minutes to run. And we hear the two different colors. So I should tell you what's going on. So we have three different colors. Purple is the standard method. What I'm showing here is 10 different runs. So you can get a sense of how stable is it over different runs. And the thicker line is the median of all those runs. Okay, so, and the best fit we got over those 10 runs was 0.3396. So basically 34% of the variance. And then it's 8 hours per run, and then you multiply that times 10 is how long it actually took us to do it. Then these two lines, these two colors here are the leverage score sampling method with different numbers of samples. So the red is 2 to the 16 samples and the blue is 2 to the 17 samples. Now, more samples does cost more, but because it's more accurate, it can actually take less time overall. So it converges in fewer iterations. And so what we found was this 2 to the 17 took only 40 minutes per run. It converged to something even better than the true algorithm, so 0.3397. We went back and plugged it into the original problem, and it was 12 times faster. And then 2 to the 16 samples was similar. And so that took about 47 minutes and got almost the same accuracy. And it was 10 times faster. Again, because each problem was, subproblem was less accurate, you didn't make as far when you took fewer samples. And so there's just sort of trying to find this sweet spot. The number of samples is one of the remaining open challenges. We have theory on the number of samples, but this is just sort of a big type bound. We need something, and involves constants we don't know. And so we need something also for practical situations. And so if we go back to this Amazon tensor, we have these 10 runs. The best fit was 0.0593, took 96 hours per run. So 10 of them took 960 hours. I can't remember if we actually did 10 in the end. I have to go back and double check the paper, but it was hard to get these done. The other ones we ran a bunch of times just to make sure everything was good. These 10 runs were, we only did 10. We didn't do any repeats. And then we did the leverage score sampling. We're just showing you the one with 2 to the 17. And these are 10 different runs. And the thick line, which you can barely see, is the median. I will point out here that there's a lot of up and down, whereas these lines are just smoothly increasing. It's actually possible to prove that for the standard method, your objective function is always getting better as you iterate. Here, we don't have that guarantee because it's random and you're only looking at a subset of the system, and each time you might actually go down a little bit. And I want to point out that we're really zoomed in here. So even though this looks like a big up and down, it's actually not so bad in the overall scheme of things, but we do go up and down and jiggle And so trying to figure out when to stop when you see that jiggling is actually maybe one of the bigger problems from a pragmatic point of view. In practice, we actually keep sort of the best fit that we have. And I should also say we never calculate the true fit with these subsample method. We have to calculate an approximate fit, and we've gone back and adjusted these fits so that we can compare it to the true one. And these details I'm happy to talk about offline. All right, so I'll wrap up there. So the paper is online. We actually just put an updated version out in December. Finally got everything sort of fixed up. So we could, and it's also been submitted for publication now. So we looked at how to make CP tensor decomposition work for really massive sparse tensors. And so matrix sketching was the answer. And then we ran into a bunch of different problems. Like, well, when you do this leverage score sampling, you get a lot of repeats. It actually took a while even to diagnose that that was sort of slowing things down. So we looked at some methods to sort of fix that. And you can combine repeated rows or deterministically include high probability rows. We also considered the question of how to efficiently sample. We sort of knew what probability we wanted to sample according to. That gave us a good upper bound, but we had to sort of figure out how to pull out those samples in a reasonable way. And then we had also to be smart about extracting the right-hand side, which we did some pre-computation to make that efficient. And when you put all these pieces together, you do get a nice big happy result, which is order of magnitude speed ups on these large scale problems. So there's still lots of open problems, how to pick the number of samples in practice. And we actually use the same number of samples no matter which least squares problem we were solving, but they're actually totally different sizes and different characteristics for each of the modes of a tensor. So you're repeatedly cycling through a bunch of least squares problems. So we probably want to be more clever about picking the number of samples. How do we determine how many rows to include deterministically? So we need some threshold for that. We just came up with something completely heuristic. But it doesn't really affect the theory per se, but it does affect the efficiency of the samples. And then we need robust stopping conditions, as I mentioned. Sampling based on the right-hand side is actually something that the theory suggests could be useful. So that might be something to consider as well. Parallelization of the method and so on. So that's the end of my talk. And I thank you for the questions so far and welcome more. Thanks.
Thanks, Tammy. That was great. Like you said, please questions in the chat if you have any. I'll start with one. So I'd just like to ask if there are any particular application areas for tensor decomposition that you're especially excited about.
Oh, okay. So yeah, applications of tensor decomposition I'm excited about. So I'm pretty excited about these higher order mixture models is one big one. So that involves symmetric tensors. And there's a lot of interesting theory out there. There's a lot of methods already for mixture models, but I haven't really seen them all converge in practice yet. So I'm interested to see that. Seems like an exciting one. And I'm always looking for people who are playing with tensors. And so most of the more interesting tensors have come to me, not me to them. So.
Okay, any other questions from the audience?
I have a question, maybe, Tammy. You know, part of this from an educational point of view is, you know, helping get these tools into people's hands is like really an important thing. And also not just get the tool in the hand as a black box, but having people have some understanding of this. Have you ever thought about putting together a little short course YouTube, and then you could put some tensor lectures together, walk through code, because this would be super helpful. Like, so, you know, because most of my students, I'd love for them to have good ways to get these things out, right? It's such an important tool to go to scale and do this efficiently, because they're often trying to solve the science problem, but I also want them to understand some of this. So anyway, just an encouragement for you.
Yeah. So yeah, I'll do two promotions. So one is I've actually started writing a textbook on tensor decomposition. I don't think version 1.0 will go into all this, but just there's actually a lot that we often brush over, and even my co-author is like, oh my gosh, there's so much that we really don't ever talk about in the shorter papers. So we're writing a book on that, which would be helpful. It'll be aimed at upper level undergraduate, lower graduate level. And then, but the other is I'm at the behest of DOE, and Nathan's been involved in some of these reports before. We're writing a report on a workshop that was recently held on randomized algorithms and pushing for sort of research moving forward. And it includes, foundational research, bringing it to applications, developing new algorithms, but it also includes, well, it'll probably include, we're still writing it, standardization, which is sort of maybe a merger together with computer science and practice, but how to bring these tools out and make them be able to be used correctly. And then I'll just add, I think a lot of times people, including myself, you try randomized methods, they don't really work, kind of get a wrong answer. They don't seem as fast as everyone said. You're sort of like, I'm not going to worry about that. It's not working. But actually, if you kind of just spend a little more time and maybe pull in some colleagues and from statistics or who have worked with this stuff before, it can make a huge difference. And you can find that these methods really can yield huge benefits, but it's just, there's some hills to climb before you get there. I think maybe a question popped up in the chat. So Rick Gibson, building on the current question for ingredient 9, you alluded to the cost of data movement and conclusions mentioned parallelization as an open issue. Can you comment about the computational platform you've used for this work, software or hardware? So I have a toolbox called MATLAB Tensor Toolbox, which is where I prototype everything. It's where we did these experiments. That's not the best computational platform. My collaborators at Sandia have written a tool called Gen10, which is a public open source thing. And there are several other open source standards, and it's still evolving. The best way to work with tensors in the large scale, especially in the sparse case, but also in the dense. But in almost any of those, it really is moving data around that costs the most. We've looked at GPUs, CPUs, distributed. It doesn't matter which one you're on. This is where it hurts. So, and we and many others who have started to look at computational issues of tensors have tried to work on that, but there's still a lot of open problems left to solve. And best ways to parallelize, I'd say, is still pretty open. I mean, that's sort of why I like tensors. There's more unsolved problems than solved ones, and a lot of room for innovation on the software as well as the algorithm side. So I don't know if that answers your question, Rick, but thank you for asking. So I did post my email. I'm always happy to get questions later, and I'm pretty Googleable if you have other questions. And we shared the slides, the PDF of the slides at the beginning, and I think Jordan, I think you have the link, or maybe Jason, I forgot who I sent it to, but they can share that again with anybody who's interested. Thanks everybody for coming.
Thanks so much. Yeah, thanks for coming. And we'll see everyone in 2 weeks.